Here we have a circuit. We have some resistive network connected via a pair of terminals A and B to a load RL. We want to find the value of RL so that we have maximum power being transferred to our load. Then we want to know how much power is being transferred, and we're being asked about the efficiency in this case. In order to find the load resistance that gives us maximum power transfer, recall that the requirement there, the condition, is that the load resistance should be the Thevenin equivalent resistance of our supply circuit. So in order to figure out what the load resistance is, we need to find the Thevenin equivalent circuit of our supply. And we have steps to find the Thevenin equivalent circuit as well. So we'll use our standard method of finding the open circuit voltage and the short circuit current, and calculating the Thevenin equivalent resistance so that we can find the load resistance and we can pursue these other questions. So the first thing we'll do is find the open circuit voltage. We'll do that by drawing the supply circuit without the load, with an open circuit instead, finding what the voltage is. So we've redrawn the circuit. We want to find VOC, the open circuit voltage, and we notice that this voltage, the open circuit voltage, is going to be the same as the voltage across the 150 ohms resistor that we have there, since there's just wire and there's just wire. Well, we have a voltage source that's connected to two resistors in series, and so we can use a voltage divider to figure out how much of the source voltage is going to fall across this resistor. We do our voltage divider, and we find that the open circuit voltage is 300 volts. Our next step is to find the short circuit current, and we'll do that by redrawing the circuit, but with a short circuit connecting the terminals instead of the load. Here I've redrawn the circuit. I have my short circuit connecting my terminals A and B. In this case, notice that we have shorted out the 150 ohm resistor. We've essentially put 150 ohms in parallel with 0 ohms. What that does in practice is eliminates that resistance. The equivalent resistance of 150 and 0 is just 0. And so we have 360 volts being applied to 30 ohms, and that's our complete circuit. And so our short circuit current in this case is going to be our 360 volts divided by 30 ohms, which would be a total of 12 amps in this case. Finally, we want to find the Thevenin equivalent resistance. In this case, what we're going to do is deactivate, because we only have independent sources, we can deactivate all of the sources. We'll redraw the circuit with the sources deactivated, and we'll look in the terminals A and B, and we'll find that Thevenin equivalent resistance. Here I have deactivated the voltage source. I replaced a voltage source with a wire because a short circuit has 0 voltage. I'm looking in these terminals A and B, and I want to see the equivalent resistance, and I see that my 30 ohms and my 150 ohms are in parallel with one another. If I put those two in parallel, then I'm going to find a resistance, an equivalent resistance of 25 ohms. I want to check my Thevenin equivalent resistance should also be my open circuit voltage divided by my short circuit current, and indeed 300 divided by 12 is also 25. So I checked that value twice and I got the same value, so we can be confident that that is correct. And so if my Thevenin equivalent resistance is 25, then my load resistance here should also be 25 ohms for maximum power transfer. So that is part A of this question. In the first part of this problem, we investigated the supply circuit. We found the open circuit voltage, the short circuit current, and the Thevenin resistance. And we know that the load resistance that is required for maximum power transfer is for that load resistance to match the Thevenin equivalent resistance of the supplying circuit. So we're able to find that value. The second part of this question asks about finding the actual maximum power transferred. So here we know what the resistance is, but we need to know how much power is being dissipated by that resistor. If we're interested in the load resistance, it doesn't really matter what circuit we have connected to it, so we might as well use the simplest possible circuit. We might as well use the Thevenin equivalent circuit connecting here to find the resistance of the, to find the power delivered to the load. So I can go ahead and draw the load resistor connected to our Thevenin equivalent. We see here connected to our Thevenin equivalent circuit, we have our load, if we want to know the power being dissipated by this load, we can consider the voltage that's being applied to that known load resistance. And the voltage that we have here, we can find that from a voltage divider. It makes sense if our load resistance is matching our Thevenin resistance, then each one of these would get half of the overall voltage from the source. Then the power delivered to the load is going to be the voltage delivered to the load divided by the load resistance. And we can find that value to be 900 watts. Note here that if we made the same argument based on this Thevenin equivalent circuit, we would have 900 watts being dissipated by the Thevenin equivalent resistance as well. However, if we consider the percent of power being delivered from the 360 volt source, the original source, we can't consider the Thevenin equivalent circuit, but we need to consider the full original circuit, because the more complicated the circuit is, the more opportunities for waste of power there's going to be. So if we're considering this circuit now instead of this one, the power being delivered to the load here is going to be the same as the power delivered to the load there, because the outside of this supply circuit is going to be the same. The load is going to see the same voltage and current and power regardless of what it's connected to, but what we see here isn't necessarily the same as what we're going to see here. So if we're looking for the overall efficiency of the circuit, we need to go back to the original circuit here, but we know what the voltage and what the current are over there, and we can use that to our advantage. So the first thing we'll do is redraw this circuit here, and we'll use our known values. Here's our original circuit. We haven't investigated this part of the circuit yet with the load connected to it, but we know that everything we found for the load over here must still be true over here. So we must have a load voltage of 150 volts. We found that, and so that still has to be the case. And then by the same token, we can argue that there must be a load current of 6 amps feeding our load. And so if we're looking for the efficiency of the circuit is going to be the power delivered to the load, which we're told is we found earlier is 900 watts, but we need to compare that to the power being supplied to the overall circuit, which in this case is coming from this source. So we have the voltage at the source. If we want the power being delivered to the circuit by the source, we need to know the current flowing from that source. So from here we can see that we've got 6 amps flowing to the load. We have 150 volts across the load, but this 150 volts is also being applied to a 150 ohm resistor. And so since these two are in parallel, these ends are connected by wire, those ends are connected by wire, they must have the same voltage between them. So if you have 150 volts here being applied to 150 ohms, you'd have a current of 1 amp flowing through that resistor. In order to supply 1 amp here and 6 amps there, we would need 7 amps flowing in, and so that 7 amps would be the current flowing through this voltage source. So the power from the source is going to be the voltage divided by, or multiplied by the current, which in this case is 2,520 watts. Then the efficiency of the overall circuit is going to be the power delivered to the load divided by the power supplied by the sources, in this case just that single source. So we'll have 900 watts ends up at the load, 2,520 watts is put into the circuit, and that comes out to be 35.7% efficient. So it looked like it was 50% efficient there, but this is misleading. You can use the parameters for the load, but you can't use the parameters for the Thevenin circuit. You have to go back to the original circuit, and we see that there's more power wasted in the original circuit, so the overall efficiency is less than it would have seemed at the very beginning.